This lesson is part 7 on related rates. So our objective is the same. We're going to solve a related rates problem. So I'm going to start off first with the change in angle problem. Okay, and this example here talks about a spy that's tracking a plane. So you have a spy tracking a plane that's flying at an altitude of 2 miles and at a constant rate of 160 miles per hour. Now there's a camera on the ground that's following the plane as it flies away from the plane. This is very important here. Now how fast must the camera rotate to keep the plane in view when the camera is pointing up at an angle of pi/3? Alright, so let's go ahead and get started with our diagram. I'm going to label a point on the ground as C for camera. And we know that the plane is flying above the camera at an altitude of 2 miles, but it's also flying away from the camera. This is a really important detail, okay? The distance between your camera and your plane will always be increasing. So let's go ahead and draw in a right triangle here. And P, the point up here, represents where your plane is at. And we know that this vertical segment here is always going to be 2 since it's flying at that altitude of 2 miles. And then we can also label this segment down here at the bottom of our triangle as x. Now x represents the horizontal distance between your camera and your plane. And it's very important here that this distance will always increase, right? Because it's flying away from the camera. So when we talk about dx dt here, they give that to us in the problem. They tell us that that's 160 miles per hour. So if the plane had been moving towards the camera, then this would be a negative rate, but because it's flying away from the camera, x will always continue to increase, so that rate of change here will be positive, okay? So it's really important for you to pay attention to those little details, because if you use the wrong sign on your rate, the rest of your problem isn't going to make very much sense. You'll get an answer that doesn't make a lot of sense, so you have to make sure your rates are always consistent with how the diagram should be drawn. All right, now we're interested in finding how fast that camera has to rotate in order to keep the plane in its view, right? So we're trying to find d theta dt, okay? That's what we don't know. We know that theta is going to equal pi/3 when we want to figure out how fast it has to rotate, but this is so far all of the information from our given problem. So now we can go ahead and try to set up an equation. So just by looking at what I have in the diagram here, I see that relationship between theta and x here. The tangent of theta is going to equal 2/x. So this is a general equation here that's going to relate my variables. Now once we have that equation, remember we want to differentiate it with respect to time. So when I take the derivative of the tangent of theta with respect to time, that's going to be secant squared theta times d theta dt. And on the right hand side, when I take the derivative of 2/x with respect to time, that becomes negative 2/x squared times dx dt. All right, so this is my derivative here using implicit differentiation. So very important, we always start with our diagram and then find our equation, then we go ahead and differentiate our equation. So don't substitute values in yet. Alright, so now let's go ahead and try to isolate d theta dt here. We could divide by secant squared theta on both sides, but instead let's just look at that as 1/cosine squared theta times d theta dt, right? That's equivalent to secant squared theta. That way we only have to multiply by cosine squared theta on both sides. It's a little bit easier to look at it that way. So algebraically here, hopefully you're following, we get d theta dt is equal to negative 2 cosine squared theta over x squared times dx dt. Now at this point we can go ahead and start substituting in known values. Alright, so d theta dt will be found if we take negative 2 times the cosine of pi/3 and square that value, okay? And then divide that by x squared. Now x is something we're still missing, okay? So let's go ahead and try to find x. So we're going to have to come back to this equation here in order to find x when theta is pi/3. So we're solving tangent of pi/3 is equal to 2/x. In other words, x is equal to 2 over the tangent of pi/3. Now the tangent of pi/3, that's just √3, so we have x equals 2/√3. Okay, so by plugging that value in here, let's go ahead and just make that substitution. 2/√3 squared. I'm going to go ahead and pause and then just evaluate this. Oh, I forgot to plug in dx dt, sorry. That's positive 160. Alright, so after we evaluate, d theta dt will equal negative 60. Now the units here are going to be radians per hour. Okay, so let's talk about why we have a negative rate here. Now this does not mean that it's a negative angle measure. It just means that theta decreases with time. So if we take a look at our picture here, we've got, the camera and the plane and theta here. So as the plane through time continues to move horizontally away from your camera, so in other words, x is increasing here. Well, theta, if we just draw another picture, you can clearly see theta must decrease, right? So d theta dt is negative to indicate that that angle decreases with time. All right, example 2 is going to be another related rates problem that uses the Pythagorean theorem. So this time it's going to be a little bit more complex than the latter problem that we saw yesterday. So it says here, at noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. We want to know how fast is the distance between the ships changing at 4 p.m. All right, so let's go ahead and get started with our diagram. We know that these two ships are 100 kilometers apart. Ship A is to the west of ship B, which means ship A should be to the left here and ship B is on the right. So let's label the distance between those 2 points as 100 kilometers. Now, we also know that ship A sails south, so it's traveling south, and we know the rate at which it's traveling, but let's go ahead and label this segment here. Since that segment is going to change, we need a variable to represent that. We'll label that x. Now we know already what dx dt is. That rate here is going to be 35 kilometers per hour. Now make sure you know that this is positive, okay, because x is increasing, x is not decreasing, so because it is increasing, regardless of the fact that it's moving downward, it's still a positive rate. Now, we also know that ship B here is traveling north at a rate of 25 kilometers per hour. Let's go ahead and label this segment here, the distance that ship B has traveled. We'll label that y. So we know dy dt here will also be positive, 25 kilometers per hour. And the reason why it's positive, again, is because y continues to increase with time. All right, now we are asked to find how fast the distance between the ships is changing at a specific time. So let's represent in our diagram here the distance between the ships. Well, that's going to be from this point to this point here. Okay, so this is some distance. Let's call that segment here z instead of d because I don't want to do dt again. So this will be z. Now, based off of your diagram, you can still relate x, y, and z, even though it looks like it's two separate triangles here. Let's go ahead and just redraw this. Okay, and create this segment here, which is also going to be 100 kilometers, and then we can just use that x value over here. So this distance here is also x. So now we have a nice little diagram that relates x, y, and z together. So now we can come up with an equation. Real quick though, we do want to find dz dt, right? That's what we are asking to find, dz dt at 4 p.m. Okay, so this is another important detail here. So let's go ahead and create an equation. We know that x plus y, that quantity squared, plus 100 squared should equal z squared. All right, so if we go ahead and try to differentiate this equation here with respect to time, we'll definitely have to use the chain rule. When we look at x plus y, that quantity squared, and try to differentiate this with respect to time, we end up with 2 times x plus y to the first power. And then we have to multiply that by the derivative of the inside, which is going to be dx dt plus dy dt, okay? Then if we take the derivative with respect to time of 100 squared, that's just 0, so let's go to the right-hand side. So the derivative of z squared with respect to time will be 2z times dz dt. Now we want to isolate dz dt, right? That's what we're asked to find. So if we were to divide out 2z here, let's just do it like this because I'm a little lazy. These 2's will cancel, so we're left with x plus y times dx dt plus dy dt all over z, okay, equals dz dt. Now all we have left is to substitute in our known values. Now at this point we're missing quite a bit of information because all we really know are the values for dx dt here and dy dt. We still need to find x, y, and z. So if we want to find x, x represents the distance that your ship has traveled, ship A. So ship A is traveling right now at a rate of 35 kilometers per hour. So if we want to find x, we're going to take 35 kilometers per hour, the speed here, and multiply it by the time that it's been traveling. Well, it's been traveling since it's gone from noon till 4 p.m. here. It's been traveling for 4 hours. So we're going to multiply that by 4. We end up with 140 kilometers. Now for the segment y here, which just represents the distance that ship B has traveled in those 4 hours, here you're going to take 25 kilometers per hour Multiply that by 4 hours. So at 4 p.m. it's traveled a total of 100 kilometers. Now to find z, this you can just use your diagram, or you can come back to this equation here and just go ahead and plug in to find z. So z is going to be the square root of 100 plus 140 squared plus 100 squared. Okay, so if you go ahead and you just plug all of these things right back into the equation, I'm kind of lazy, I guess I should pause and just do this for you real quick. Alright, so as you can see, after I plug in those values, you end up with a pretty nasty expression here that you're probably going to want to use a calculator for to simplify. Now, I went ahead and I worked this out already. You end up with 14,400 divided by 260. Now, that is something that doesn't really simplify nicely to something in terms of kilometers per 1 hour. It does simplify to 720 kilometers per 13 hours. But that's not really a typical rate that we would want, so you probably just want to give a decimal approximation in this case. So that's approximately 55.4 kilometers per hour. So this is the rate at which the distance between the ships is changing at 4 p.m. All right, in example 3, we're doing a spin-off of the leaky container problem from yesterday. So in this case, our trough is being filled with water, okay? So as opposed to leaking water, it's now being filled with water. So it says a trough is 12 feet long and 3 feet across the top. Its ends are isosceles triangles with altitudes of 3 feet. If water is being pumped into the trough at 2 cubic feet per minute, how fast is the water level rising when your height of the water is 1 foot deep? Now, off to the side, you already see a diagram, okay, that is depicting what's happening in this problem. We're just missing a couple of the rates. Now, the one listed up here is the change in the volume. So dV dt here is positive 2 cubic feet per minute. We also want to know dH dt. So we're looking to find dH dt, okay, how fast the water level is rising when h is equal to 1. All right, now when you come up with an equation that will relate all of the information here and your variables together, you're going to want to use the volume of a prism. So this is a little bit of review from geometry. Now when you take the volume of a prism, this is for any prism. In our particular example, we have a triangular prism because the base is here would be a triangle, and it's a prism because the sides, the lateral faces here are all rectangles. But anyhow, when you take the volume of any prism, you're always going to take the area of the base of your prism, and multiply it by the overall height of your prism. Okay. Now in this particular case, like I said, this is a triangular prism, so we're going to have to take the area of a triangle, that's our base, so we're going to do 1/2 the base of that triangle times the height of the triangle, and then we'll multiply it by the overall height of the prism. So don't get this confused with the height of the triangle, it's a different height. So I'm going to label this still with height of prism. So the reason why they're different, okay, so the volume here of our shape is going to be given by this equation, but the reason why these two variables here are different is because the height of your triangle, that's the altitude, that's 3 feet, right, this segment here. The height of your prism, you have to kind of imagine that you're going to invert this trough so that it's resting on its bases. So if it was resting on this particular face here, that base, then the overall height is given by this segment length, or this segment length here, which is 12. All right, now when we look at this equation here, we can actually make a substitution in for the height of the prism because that quantity does not change. It doesn't matter how much water you pump in and how much time has passed, because the length of that trough is going to stay consistent. So it doesn't matter if the level of the water in there is a foot or 2 feet or 3 feet, it's going to stay the same consistent value, 12 feet. So I'm going to go ahead and make a substitution here. We have 1/2 times the base times the height of the triangle. So these are both related to the triangle's height. And then the height of the prism, like I said, is going to stay constant at 12. All right, now if I simplify this a little bit further, we have 6 times b times h. So at this point, what we could do is differentiate this equation with respect to time. That's normally what we would do. But in this case, I have a product on the right-hand side, and I don't want to have to use the product rule here. So what I'm going to try to do is eliminate one of those variables and try to write it in terms of just one variable on the right-hand side. Now, we're trying to find dH dt. So what I'm going to try to do is eliminate b, so I can rewrite this equation here in terms of just h on the right-hand side. All right, now to find the relationship between b and h here, I'm going to just draw in that triangle real quick. I know that this altitude is always 3 feet. Okay, the height of that trough is 3 feet. The overall width here is going to be 3 feet as well. So the base is a total of 3 feet here. But this little segment here is 1.5 feet. Okay, so let's label that as 1.5 feet. Now the reason why I'm doing that is so that you can see, even if I create another triangle within this triangle here, so let's say the water level is here, well, I'm dealing with a similar triangle, right? So whatever this side here is, this little segment, just half of the overall triangle here, that's going to be half as big as this height here of that new triangle. So the relationship between this segment and this segment is always, half as big. So when we're looking at the overall base, this overall base is equal to the overall height. Now, if b is equal to h, that means that in this equation here, I can make a substitution. So we have 6 times h squared is equal to v. Now we can go ahead and differentiate this with respect to time. So we have on the left-hand side dv dt. On the right-hand side, we'll get 12 times h times dh dt. So if we want to isolate dh dt, because that's what we're trying to find, right? dh dt is our unknown. Let's go ahead and isolate that by dividing out the 12h. So we have dv dt over 12h. That will give us dh dt. So now we can go ahead and make some substitutions. We actually know everything that we need to know. dv dt here is 2 cubic feet per minute, and h is 1 foot. So just by substituting in, we end up with 1/6. Now the units here are going to be feet per minute. So the rate at which the water level is rising when h is 1 foot deep. So when your water is 1 foot deep, the water is rising at a rate of 1/6 of a foot per minute. All right, in our last example, it says that water is being poured into a conical reservoir at the rate of pi cubic feet per second. Now the reservoir has a radius of 6 feet across the top and a height of 12 feet. At what rate is the depth of the water increasing when the depth is 6 feet? Now the basic premise of this problem is similar to example 3. We're still filling up a container. So here the container just happens to be a cone. So let's go ahead and draw in our cone. Now the radius of this cone here, that's 6 feet, while the overall height of the cone is 12 feet. Now we know that water is being poured into the cone, and it's at a rate of pi cubic feet per second. So this represents the change in the volume of that cone. So dv dt here is pi cubic feet per second, and this is positive because we are filling the cup, or the cone. Now if we want to find the rate at which the depth of the water is increasing, really what this is asking for is dh dt. Okay, so let's label h here. Let's draw in some water. So h is this segment length here, and we want to know dh dt, okay, when the depth or the height is 1. Now to come up with an equation that will relate our variables, let's look at the volume of this water. Now the volume of the water is the volume of the cone. So in this case, the volume of a cone is found by taking 1/3 times pi r squared times h. Now, once again, we end up with a product here of 2 different variables, and when you differentiate this, just to avoid that, you can try to rewrite this equation in terms of just one variable. So that's what we're going to do here. We're going to look back at this diagram. Let's use similar triangles. So we have that big triangle here, radius 6 and a height of 12. And if we just, fill this cup here, or fill the cone here, that water level now creates a new triangle, and it has a radius of r and an overall height of h. So just by similar triangles, 6 over r, or r over 6, okay, is equal to h over 12. In other words, r is equal to 1/2 h. So I can make this substitution now, okay, in for r. So the volume of the cone is equal to 1/3 times pi times 1/2 the height squared times h. So if we go ahead and simplify here, you have 1/3 times pi times 1/4 h squared times h. And if I just simplify a little bit further, that gives me 1/12 pi times h cubed. So now I can go ahead and differentiate this equation here with respect to time. Okay, so on the left hand side we have dv dt, and on the right hand side, if we just bring down that 3 and multiply out in front here, you end up with pi over 4 h squared, and then you have to multiply that by dh dt. So here is our equation. Now we can go ahead and isolate dh dt, because remember that's what you're trying to find. So dh dt is equal to, let's see, multiply by 4 over pi here. So we have 4 over pi h squared times dv dt. All right. Now at this point, we can go ahead and substitute in our known values. So dh dt, okay, when you're looking at the height being depth of 6 feet here, that's going to be found by taking 4 over pi times 6 squared, so the depth is 6 feet, multiplied by dv dt, which is pi cubic feet per second. Now just by simplifying here, the pi's will cancel. 4 over 36 is 1/9. So we have dh dt is equal to 1/9. Now let's make sure our units are correct. This is going to be feet per second. So we're looking at the depth of the water is increasing at a rate of 1/9 of a foot per second when the depth of the water is 6 feet. Alright guys, that is the end of the lesson. So I tried to give you some examples that would help you with your homework. Obviously no two examples are the same, so a lot of this is going to come from your ability to problem solve. So the more practice you get, the better you're going to be at it. So make sure tomorrow you ask a lot of good questions. Nice job. See you tomorrow.